Welcome to FNet Silica's We Talk IoT. We'll chat with innovators, experts, and business owners to learn how they are implementing IoT and using data to create new business opportunities. I am your host, Stephanie Ruth-Hader. Recently, the Advanced Electronics Challenge took place at Electronica, an event organized by FNet Silica in cooperation with by Startup, Altium, and Renesas, where startups and young innovators presented their hardware-based product ideas. I am thrilled to be joined by Timo Fromm and Rudolf Borchardt from CiX Greentech today, a promising startup based in Erlangen, Germany. CiX secured the third place in the competition, congratulations guys, with their groundbreaking water purification technology. They have a ready-to-connect module that uses electricity to destroy microcontaminants like, for example, pharmaceutical residues, hormones, bacteria, viruses, and persistent chemicals as well, such as PFAS, often referred to as forever chemicals. So today we will talk about their journey through the challenge, the technology behind their solution, and how innovations like theirs are helping to create a cleaner, more sustainable future. Timo, Rudolf, welcome to the show. I'm excited to have you today.
Thank you, Ruth.
Thank you, Ruth, for having us.
Would you like the chance to introduce yourselves? Can you tell us a little bit about CiX Greentech and how your journey started?
Yeah, I think you already introduced us quite well, Ruth. So all the basic information that one needs to know about us are given. As CiX, we work to protect and improve water quality worldwide by offering a cost and energy effective purification system to break down pollutants in water, especially those that you mentioned. We're talking about bacteria, viruses, drug residues are often found as pollutants in water. And in the last years, more and more focus has been laid on the PFAS pollution, and we are glad that we can offer a system that is kind of like a building stone in order to tackle the PFAS pollution problem.
Yeah. What does PFAS stand for? Sorry to interrupt you.
Per and polyfluorinated alkyl substances.
Okay.
Quite chemical term. Basically describing the molecules that are part of this group of molecules. So it's not just a single one, it's a whole group of molecules that are combined under this term of PFAS.
Okay. And how did your journey start? How did you come up with this idea?
So basically, we studied both nanotechnology at the FAU in Erlangen, and after our master thesis, we were offered a PhD position at our chair, where we were working on diamond coatings in general. So not specifically on diamond electrodes, what we are using today, but yeah, these diamond coatings. And the diamond has quite some outstanding properties that makes it a unique material for many applications. But during this PhD time there at our chair, we were kind of involved, or we were the key players, let's say so, in the development of a new kind of diamond electrodes, because the diamond electrodes itself are around like for 20 to 30 years. But till today, they are kind of only applied in niche applications.
Okay.
And their main problem is that they are quite expensive in producing, and also their energy consumption is quite high. And we try to tackle both of these disadvantages that kind of hinder their broad application.
And what motivated you to apply for this Advanced Electronics Challenge?
So basically, our team colleague, Benjamin, found about this Advanced Electronics Challenge, and we are right now a startup in the pre-founding phase, so we are not founded yet, but we have a quite good funding from the German government, the Exist Forschungstransfer, so research transfer funding, And yeah, we are quite good in producing these diamond electrodes and producing treatment modules with these diamond electrodes, but we are not really good in the electronics part. And we noticed for our electrodes that it's quite crucial to have a good control for our modules and also to extend the lifetime of our electrodes with a good control unit. And yeah, when Benjamin found out about this advanced electronics challenge, we immediately decided that might be a good chance to get some expert information about how to get a good control unit for our treatment modules.
And to kind of add to that, as a startup, one comes across such programs pretty often. And we have taken part in quite a few of such challenges or accelerator programs, as they are called often. And we have made quite good experience with that. So in every case, you learn something, you get to know people, you kind of like can have an exchange on how certain problems have been overcome during the journey to being here. And in now, as we are a few years into our journey, we really kind of like selecting or cherry picking those events. And this has been one where we applied for because we thought it will benefit us along the way.
What were some of the highlights and key challenges of participating in the challenge?
Yeah, there were different ones. So like in the beginning, there was this, introduction phase where we get to know all the different kind of electrical components and different participants in the Advanced Electronics Challenge. And it was really helpful to get a better understanding what we might need and where we can ask for more information and get an expert opinion about certain topics. And it was always nice to have someone who we can contact with Afnet Silica, where we could ask, for example, Mike to help us with a certain problem to further develop our control unit.
So let's dive into your solution. I'm excited to learn how exactly does your water purification module work.
So that's quite a trick system, to be honest. It's a quite easy process. The foundation of the process, basically. So what diamond electrodes can do is basically take an H away of the H2O molecule that makes up water. And it takes away one H and leaves behind a OH radical. And it's important to mention that it's a radical, not an ion, which some people with a bit of background knowledge may assume. So it's a radical, and chemical radicals, they are known for their high reactiveness. So the diamond electrodes produce those OH radicals in water, and those radicals react with anything that's around them. And basically, by reacting with them, the reaction partners are oxidized and thus removed from water. The cool thing is, this process only is possible, or basically only is possible with the use of this diamond surface. A few other materials, a few other reactions can trigger this reaction as well, but diamond surfaces are quite good to make this process. And other materials are not able to do so. For this reaction to happen, you need to apply a voltage to those diamond surfaces. And if you apply a voltage to materials in water, what generally happens is you split the water into oxygen and hydrogen. That's called electrolysis and is used, for example, to produce hydrogen gas. And only with the use of diamond, you get those OH radicals, which makes the material so unique, basically. And those radicals react with the pollutants in water, and by the reaction, they get oxidized and are removed from water or broken down.
Okay.
So it's not
I
like
really wish you would have been my chemistry teacher in school.
Would you?
Yes,
I'm
actually,
not
I
so
would
sure
have.
about that.
Yes.
Okay,
I
thanks.
could follow you. I think I understood the process.
Good.
Yeah. Which is a new experience for me with chemistry. Yeah.
Okay. So if the startup wouldn't work, I can think of a
Yeah.
second career path.
I hope you don't have to.
I hope so too.
Yeah. Sorry, I think, Rudolf, you wanted to add something.
I just wanted to add a short note. So it's the diamond electrodes do not filter or something like that. So we don't just keep back the pollutants from flowing through our module, but we really destroy them on their atomic basis, basically. So it's not like just keeping them back and then afterwards we have to replace the filter and burn the filter, for example, with the pollutants, but really oxidizing them where they are within the
And
water.
there's no waste material you need to take care of. It's just vanished,
Exactly.
gone. Yeah,
There's
so that's
no
really
waste
cool.
material, and you don't need to add further chemicals to the reaction. So the cool thing is you put those electrodes in water, and they, by the push of a button, they start this reaction. And if you switch them off again, the reaction stops, and there's no additional chemicals that you need to pour inside in order to trigger something along the way.
So at the same time, it's not only efficient, it's also super safe because the chemicals or the pollutants are just destroyed. And then the water is safe for drinking or for reusage.
Yeah, sometimes it's quite difficult to give there a general saying about how safe the water is.
Okay.
Because the pollutants within the water can be different quite much, and also what happens with some ingredients of the water can also be quite difficult to predict in advance. But we as a startup focus right now more on the wastewater treatment, kind of to remove the micropollutants from the wastewater, so it's safe to discharge it into the environment, or in the best case to reuse process water within some industry processes. But in general, the technology would also be applicable for drinking water applications. But as a startup, it's quite difficult to fulfill all the regulations that are necessary there. So that might be something in the near future, but not right now for us.
Okay. This might be a no-brainer for you, but just to give some more context, why is it so important to remove microcontaminants from wastewater?
So generally, it's the water usage is a closed loop, and has been forever. We take it from nature, the water. We use it, and we give it back to nature with all the stuff that's inside. And in the long run, as it's a closed loop, the water gets back to us. And hence we invented water treatment as a general, right? To purify the water that we give back to nature. And a few stages have developed of water purification. The general communal water treatment uses 3 stages of water treatment. And those 3 stages work quite nicely. The water looks quite clear at the end of the treatment process. But clear water doesn't have to be necessarily to be non-harmful to nature or to humans. So those micropollutants, they are just not visible. And for a long time, the notion was the water is quite good to give back to nature, quite good to use. But the analysis methods have advanced so drastically that that now we are able to measure the concentration of those micropollutants. And the surprise was basically, oh no, like the limit values that we have set ourselves are drastically over polluted in comparison to the limit values that we have. We give those to nature, And those micropollutants, like we mentioned, drug residues, for example. There are, for example, hormones. Hormones come from drugs that people take in, and those in very small concentrations already have the power to have a high influence on every living being, turning, for example, whole frog populations into becoming only female frogs during their evolution or during their growth. Also, fish populations are influenced by that, for example. And down the line, this will influence humans as well. And the PFAS pollution is kind of like a separate topic, as this is only a man-made substance. It has been produced since the 1940s in large quantities for industrial processes. Very many industrial processes heavily rely on the use of PFAS. And the problem with those is if they get into nature, nature doesn't have a process to break them down. So once such a molecule is in the environment, it stays there forever, hence the term forever chemicals, right? And we need to find a way to get those pollutants out of the water in order to not have a bad influence on the living beings on Earth. And this is why, for example, the EU has made it mandatory to have a 4th purification stage now. And we are one of the technologies that have the capability of destroying those micropollutants.
Yeah, when you just mentioned the effect it has on frogs and fish, a Simpsons episode with a 3-eyed fish comes to mind, if you know that one.
That's not too far-fetched. Yeah,
that's quite scary.
Yeah.
You mentioned at the beginning a control system that you have implemented. Can you explain a little bit what role does it play?
Yeah. So basically, as Timo already mentioned, our electrodes need an electrical current to operate. So this is a DC voltage, and we want to operate our electrode modules in a most efficient way, because this was one of the disadvantages the former diamond electrodes had. And so we don't just want to apply an electrical current and leave them running in a wastewater, but we also want to kind of implement an on-demand treatment operation mode so that we can adjust our power input to the actual pollutant concentration within the water. And so we try to develop a control unit that has the capability to have sensor values as a control unit, so we can adjust our power input according to the pollutant concentration. And during the challenge, we did it with a CO2 sensor that kind of measured the CO2 produced by our diamond electrodes by the oxidation process. Because as Timo already mentioned, we oxidize basically everything within the water. And most of these molecules and bacteria and stuff like that is made out of carbon atoms. And these carbon atoms get oxidized to CO2. And so we can measure the CO2 that comes out of the water. And this is one of the first sensors we used during the challenge to measure how much CO2 is coming out. And as long as CO2 is coming out of the water, we know we have to treat the water further.
Okay, that's cool.
In the future, we want to add different sensors depending on the kind of wastewater we are treating. So in the best case, we can really adjust and fine-tune the energy input. So it's on-demand treatment and not an over-treatment all the time, or an under-treatment in the worst case, so that still pollutants get out into the nature.
Are you thinking about other sensors? What else would make sense?
Yeah, we're kind of figuring out right now what might be good sensors to implement as well. So this could be a pH value, for example, but there's no rule of thumb to say, this sensor works for everything. because the kind of pollutants that are in the water are quite different from water to water. So there might be also like spectroscopic sensors, a temperature sensor in general to supervise or to have a look at the process itself, if it's running efficiently. But right now we are figuring out what sensors might be a good add-on for our control unit.
What industries or areas would benefit most from your technology? Is it only wastewater treatment, or have you thought about others as well?
So it can be used for all different kinds of wastewaters, and there's no specific industry where we see our modules working the best in, because the wastewater in general is so different from company to company. So it might be that like a textile finisher has more similarities to a butcher industry than another textile finisher has with another textile finisher. So it's quite difficult to have a general industry in focus. But we try to look more on what kind of pollutants do specific industries have in the water, for example, the PFAS, and try to figure out, these industries have the biggest problem with the PFAS, for example, and then tackle these and more in
It
focus.
also seems that your solution is so flexible that is it also possible that you don't even know what pollutants are in the water and you would be able to purify it? Does that work?
That's hardly the case, to be honest. So mostly the people know what's in the water, or what the pollutant they want to get out is. It's often dependent on what else is part of the water matrix, as we call it. So the whole substances that are in water, and those differ from region to region. For example, minerals or salts that are generally in groundwater, for example. But the potential applicants, they usually know kind of like what's the problematic substance in water. But it's quite flexible in treatment as long as we're talking of an organic molecule. So everything that relies on carbon chemistry is basically able to be removed with our electrodes.
Okay.
And as Rudi mentioned, they can be quite diverse. But as they or many industries heavily rely on process water, which means they take in water, and along the way, some substances are gonna be polluted in the water. We now offer a way to potentially close their water loop. So it was proven that with diamond electrodes, for example, you can just run water in a closed cycle, which is quite interesting because in former times, what you were doing usually is you took in a load of water, you polluted it, and at the end of the day, some recycling company had to come, take the water, and then it had to be discharged somewhere or to be taken care of in a special facility, which often means the water is burned. And burning water is never going to be an energy efficient process. So it's not a modern tech to tackle this problem. So closing water loops is kind of like one of the interests that potential customers come to us for.
And what is next for you for CiX Greentech after the competition? Are you already working on pilot projects or partnerships you are allowed to talk about?
So we can't tell any names, but we are right now building a bigger treatment module or modules that we can really bring to potential customers and test it in real life applications. And we also have a small treatment system running in a wastewater treatment plant as a fourth purification stage to see if it's really a technology that's applicable as a fourth purification technology and to compare it with already existing other technologies like activated carbon or ozonation. And that's what we are focusing right now. So really to build bigger scales to prove to potential customers that it is a scalable technology and that we hopefully could tackle all the difficulties that were hindering the diamond electrodes to be applied for wastewater treatment.
Cool. Very nice. And any other future plans? We've mentioned that it might in the future also be used for safe drinking water solutions. Could it be applied? And now you're looking at scaling up, but are you also looking at how it can be applied in smaller and decentralized systems?
We do. We do. There's one promising approach. From the beginning, we were always thinking in big plants because oftentimes the water volumes that we are talking about are quite huge. So you need larger systems in order to be able to treat those. But along the way, also a few interesting discussions have come up, also with customers who see the problem, or they have a problem in another scale, and quite smaller electrodes would also be applicable for their solution. So interesting that you are asking, because we are right in this week have been in talks with the potential customers, and they want kind of like electrodes in the size of a USB, a USB device. So that's the other way around. It's also the topic is scaling up because the electrodes are smaller, but the amounts of electrodes that they want to have is just quite large. So they want many small ones. It's another topic of scaling up, but it's also another size to think in.
Exciting.
It is.
If you had to pick a song for the soundtrack of this episode, what would it be?
What's the interpreter? There's something in the water. Fromm.
And she's called like Brooke Fraser, right?
Yeah, that could be.
Yeah. In that case, we would go with Brooke Fraser, Something in the Water.
Very nice.
That just fits. Yeah.
That is perfect. That brings us to the end of today's episode. A big thank you to you, Rudolf and Timo from CiX Greentech, for sharing your insights and telling us about your exciting technology. It'll be really interesting to see where you're headed in the next years. I hope to have you again on the show and learn about all the projects you have now been working on in more detail. To me, it's so inspiring to see how startups and innovators are tackling some of the world's toughest environmental challenges with smart hardware-based solutions. So if you want to learn more about the Advanced Electronics Challenge or CiX Greentech, check out the links in the show notes and pay attention to the upcoming episodes where we will talk to more participants. Thank you for listening to We Talk IoT. Until next time, stay curious and keep innovating.